Greetings. This is the first of several lectures about optics that'll help you for next week's lab. And this is basically an introduction. And I want to be talking about Snell's law. And what this refers to is to the fact that light changes speed in different media. And remember, light travels at the speed of light. The speed of light is going to be different depending upon what the light is traveling through. Now, in a vacuum, let's see, create a new slide here. In a vacuum means in the absence of any gases or air or materials, light travels at a speed which is known as c, which is equal to 3 times 10 to the 8th meters per second. To give you an idea how fast that is, light would go around, if there were a path around the Earth, it would go around the path about 7 times in 1 second. So that's 3 times 10 to the 8th meters per second. It would go around the Earth around 7 times around the Earth per second. It's fast. Okay, now in other media, and this kind of makes sense if you think about it, light travels a little bit slower. When it passes through other substances. The reason is, you can think about it this way, the photons, the energy from the light, keep bumping into atoms, which then basically excite and release the energy, and the light continues on. So in the process of bumping into all these atoms throughout the media, light travels a little bit slower. So the ratio of speed of light in a vacuum to speed of light in some other medium or some other material that's given the symbol n, little n, and that's called the refractive index of that material, of the material here in the denominator. So n is always going to be greater than or equal to 1. Okay? So that's the first concept I wanted you to know, is that light travels at different speeds in different media, and the refractive index n tells you whether the light is traveling greater than or less than, the refractive index n is the ratio of the speed of light in the vacuum to the speed of light in the other material. So it's always going to be greater than or equal to 1. The greater n is, the slower the light is traveling through the associated material. So what does this mean? This means that if you have, let's imagine that you have material 1 right here on this side of the red line. You have material 1, and let's say you have material 2 here on this other side. This means that if you have a beam of light that's passing through here, now light, keep in mind, is waves. This harkens us back to the beginning of the semester. So imagine light traveling in this direction right here. Okay, these lines represent wave fronts. So the waves, if you could think of the waves as being like waves on the beach, they're going to have crests, they're going to have troughs. And I'm going to represent the crests by these lines that are perpendicular to the direction in which the light is traveling, and parallel to one another, and spaced by a wavelength. So this will bring back memories to the beginning of the semester. Alright, so imagine that medium 2 has an index of refraction that's greater than that of medium 1. Whoops. Okay, so it's, in other words, the light travels more slowly in material 2 than it does in material 1. Well, what's going to happen? Well, what's going to happen, actually, these wavefronts are all right here, for instance. Let me circle them in blue. These wavefronts right here are all reaching their peaks at the same instant in time because they're together in sync. So what that means is that those wavefronts that hit this material first are going to travel more slowly than those that hit it second. So in other words, right here, at this point here, this wave is traveling more slowly, so it hasn't quite gotten to where the other ones are. So it's going to be a little bit before them. It's going to be right here. Similarly, this wave, this guy here, is going to have traveled more distance in the slower material, so it's going to have its peak right here, etc., etc. So what happens at the interface is that these wavefronts bend because they're traveling more slowly. So the frequency of the light still stays the same. The speed of the light changes, so that means that the wavelength changes as well. So what we're going to see is wavefronts in this material that instead of going in this direction here are now going in this direction here. So as a result of the light traveling more slowly, the light actually bends in the corresponding new medium or new material. And this bending is quantified using Snell's law. So I'm going to relationship, and then I'll end this video and we'll do another one soon. So I have n1 times the sine of theta 1 equals n2 times the sine of theta 2. Now n1 and n2 are the corresponding associated refractive indices of medium 1 and medium 2. So what's sine theta 1 and sine theta 2? Those correspond to the angles measured from the perpendicular to the interface of the line that distinguishes medium 1 from medium 2. So if this is medium 1 here, and this is medium 2 here, this is the solid line is the boundary between them, and this dotted line is the perpendicular to that boundary. So if the light's hitting medium 1 at this angle here, theta 1 is defined to be this angle here. And theta 2 is defined to be, if let's say the light bends like that, theta 2 is defined to be this angle here. That comes about as a result of the change in the speed of the light from one material to another. Alright, so this relationship between theta 1 and theta 2 is given by Snell's law right here. And we'll talk about that in the next slide, but you'll be seeing it in the lab on Monday.